Hi, I'm Parecki. I'm really excited to be here today and talk to you all about how to think about OAuth security. So we're going to start with some background about OAuth. I'm going to talk about how we got here, why OAuth is useful, what problem it's solving, and throughout the course of this presentation, we're going to look at some of the detailed things about OAuth that make it less secure or have been serious problems in the past. And we'll learn how those have been addressed in the current updated version of OAuth 2. So OAuth 2 was originally published in 2012, and that was to replace the version of OAuth 1 that had been already deployed in a few places. OAuth 1 had a few significant problems that either made it limiting in certain situations or were just outright impossible to use securely. So OAuth 2 really started from scratch, from the ground up, tossed everything out the window, and now we have a completely different way of dealing with OAuth compared to OAuth 1. We don't really talk about OAuth 1 much anymore because it's considered legacy and deprecated, and the industry has moved on to OAuth 2. Before we get into OAuth 2, I want to talk about what the world was like before OAuth, though. So this actually used to be very common. This kind of prompt in an application of this application, would just launch and it would ask you for your password to your Google account so that it could find your friends in your Google account, find your contacts. So it's trying to access your address book in Google, and it asks you for your Gmail account and your Gmail account password. This app would then go log into your Gmail account, use the API to get the contacts out, and then see if any of your friends were already using the application. Now, this is terrible. We know this now, right? But it was actually very common. Even Facebook was doing this. And there's many reasons why this is a bad idea. But the most obvious reason is, are you really going to trust random applications with your Google account password? So people were doing this because they actually did want the result these apps were providing, which was that they wanted to find their friends. What's wrong with that, right? But the way that this works was terrible. All this app was trying to do is actually get access to your contacts. But by giving it your password to your Google account, it has access to everything, including your email. It could even send email as you. It could go and access other Google things like your YouTube account. So what OAuth set out to do was to solve this problem. And this problem is that we're trying to let this application get access to Google contacts, but not have it access everything. And we're trying to do that in a way that doesn't involve giving this application your password. So this was the original goal of OAuth, and it started out by focusing on this sort of third-party app use case, where Yelp is trying to get data from Google Contacts, or Last.fm is trying to get data from Spotify, or Buffer is trying to post data into your Twitter account. It really started with this third-party app access use case. So at the end of the day, what these apps are trying to do is get access to data. And in order to do that, they need to get what's called an access token in OAuth. That access token isn't the data itself. It's a way the app can go and make an API request to access that user's data. So I like to think of this analogy of a hotel, where you go to the front desk, you check in, and you show the person at the front desk your ID and give them a credit card. They give you back this hotel key. This hotel key acts like an OAuth access token, where you can go walk up to a door, you swipe the key on the door, and the door opens up and lets you in. Now, the reason this is analogous to OAuth is that you, the user of this access token, don't actually need to know what's on it. It's completely opaque, right? It's just a key card that you know that when you go and use it at the door opens up. That door is the resource server or the API. That door needs to know how to read the access token, the key card, but you don't as the user. OAuth 2 sets up this framework of this way to go and talk to an authorization server, get an access token, and then go use it at an API. And OAuth defines actually several flows of different ways to go and get this access token. The end result of all of these flows is the same. So we have the authorization code flow, the implicit flow, the password, and the client credentials. The end goal of these flows is to get an access token. Once that flow is complete, it doesn't really matter which one had been used. That access token is the same and can be used the same way. So the core spec defines these flows, but the core spec doesn't actually define what an access token is. That's part of a different spec. But I want to go through just quickly what a basic OAuth flow looks like. So this is an example of the authorization code flow. We first start out with these different roles, right? We've got the user who's using an application at a browser. We've got the application that's running on a web server somewhere. And then we've got the two parts of the API, the OAuth server and the actual API server. So to start out, the user approaches the web application and says, hey, I'm trying to use this application. Please let me log in. And that's going to be clicking a button that says log in or connect with Google or things like that. The app says, great. Don't give me your password. I don't want your password. I can't do anything with it. Instead, go over there to the OAuth server and go log in there. So the app sends instructions to the browser saying, hey, go over to the OAuth server, here's my client ID identifier, things like that. So the user lands at the OAuth server, and then the OAuth server says, cool, who are you? Please log in now. And if the user then logs in, they will see a prompt that says, okay, this application is trying to access data in your account. Do you want to allow this? And if the user clicks yes, then the OAuth server generates a temporary code, which is sent back into the user's browser. And then the user's browser delivers that back to the application saying, all right, I got this code from the OAuth server. You can use this code to get an access token. Now the app can go make a post request over to the token endpoint and say, hey, this user just finished this flow. Here's the code I got. Here's also my client secret. Please give me an access token. And now the access token is delivered in that response. And now the app can go use the access token at the API. So that's a summary, high-level overview of the auth code flow. If you want to see more details about that, there's plenty of videos on the Okta developer channel where I talk about the details of these flows. So go check out that channel. Lots of good resources there. So at the end of this flow, the result is the app has an access token. And in OAuth terms, this is called a bearer token because whoever holds that token is the one that can use it, just like a hotel key. If you find a hotel key on the floor, you can pick it up and start trying doors. So that is why an access token in OAuth is called a bearer token. Now, this was actually a pretty contentious point back when OAuth 2 was first being developed, because OAuth 1's tokens were not bearer tokens. They actually required two different secrets to use. They required the client secret of the application and the secret associated with the access token that was issued. And those were then used to sign the request, and that meant that access tokens weren't able to be, picked up and stolen. There was this whole thing about should we make bearer tokens because they're simpler or should we require signing? And there was this huge fight. Anyway, what ended up happening is that access tokens got pulled out into their own spec. So there's a separate spec that talks about bearer tokens. The idea was that maybe somebody would come along and define a new different type of token that wasn't a bearer token and use that alongside bearer tokens. So this RFC 6750, this talks about bearer tokens, which basically says access tokens are a string, and here's how to use them. You can send requests with access tokens in an HTTP header. You could also use it in a post body or in a query string. Now, one of these is a bad idea, and it turns out it's this one. Access tokens and query strings aren't really safe because there's more ways where that can leak, and if it leaks, then whoever has it can start using it just because it's a bearer token. So you might be wondering, well, why didn't we use sender constrained tokens in the beginning then? Why didn't we require secrets to use these tokens? Why are we using bearer tokens? Well, one, it was just really complicated. Nobody liked the signing algorithm that was used. It was confusing and hard to do. If you don't believe me, go try to write code to use the Twitter API without using a library because it's still OAuth 1. So OAuth 2 was created to make things simpler, but the other goal of OAuth 2 was to be able to support these kinds of applications that actually can't use secrets. And that was really the flaw with OAuth 1, and which is why it isn't really used today, because there's no way to really use it safely in a mobile app or a single page app. These types of applications have this problem where they are unable to actually be deployed with a client secret. If you tried to put a client secret or any sort of API key in a JavaScript app, you will very quickly realize that it's not going to be secret for long, because someone just has to go to the website and then open up the browser, view source, and start poking around looking for the API key. And you can't hide it from them. There's just no way to hide it. Now, it's also true with mobile apps. It's a little bit more involved. You have to reverse engineer, decompile, and use tools to extract that, but totally possible, and it has been done before. In fact, if you go back to 2013, there were all these headlines going around about how Twitter's API keys were leaked because they were extracted from their mobile apps. Someone had just gone and downloaded the apps and then decompiled them and put them on GitHub. So the solution to this is, well, you can't use a secret. Don't put secrets in native apps or single page apps. And what that means is that the OAuth 1 is just out the window. There's no way to do it. OAuth 2, the flow we looked at before, required a client secret. So what are we going to do if we can't use a client secret? And that is where we get to one of the first extensions I want to talk about, which is PKCE. So the idea with PKCE is that it is a way to securely do the auth code flow that we just looked at, but not have it rely on a client secret. And again, I'm not going to go into the details of how this works in this talk because there's plenty of videos on YouTube. Again, go to the Okta developer channel. You'll find lots of tutorials and walkthroughs of how to use PKCE and how it works. But essentially, the short version of what PKCE does is when the app starts the flow, it actually generates a new secret for every request. and it uses that secret when it starts the flow, and then it requires that in order to use that authorization code, you also use that secret again. So what it means is that even if someone does steal the authorization code, it's not useful anymore because they can't have also stolen the secret. So PKCE was developed as an extension. It's an extension to the auth code flow. And one of the other things that was developed around the same time was this recommendation for how to do OAuth in mobile apps specifically. So PKCE was really designed for mobile apps, but it turns out it's useful in many other situations as well. One of the other things this spec includes is other recommendations for mobile apps, like how to use a OAuth browser on a mobile phone securely and how to deal with redirect URLs. So I mentioned that PKCE is useful outside of mobile apps as well. Let's talk about this for a second. So what do these two browsers have in common? Well, both of them don't support CORS, cross-origin resource sharing. So why is this important to OAuth? Well, CORS is, of course, if your application is served from one domain and JavaScript on the page wants to talk to a different domain, CORS needs to be configured properly. Now, why this is relevant to OAuth is because during the authorization code exchange, that application needs to go and make a post request over to the OAuth server's token endpoint to get the access token. So if we look back at this diagram, that pink line is the application making a request out to the OAuth server to get the access token. That needs to support CORS in order for it to be possible to do it from a browser. These lines are colored differently because these are two different ways that data moves around between the application and the OAuth server. The blue lines, everything is running through the user's browser. And that's the idea of using the front channel to move data between parties. The pink lines are back channel requests. And of course, the back channel is the more secure one of sending data directly from a client to a server. So with the back channel, the idea is the application makes a post request over HTTPS. It can validate the certificate. It knows who it's talking to. That data is encrypted in transit, so it can't be modified, and the response comes back in the same request. That's generally considered secure, as opposed to the front channel, where instead of actually talking directly, you use the address bar of the user's browser to move data between parties. So we're actually trying to deliver that authorization code from the OAuth server to the application, but they don't have a way to talk directly. So instead, we use the front channel to move that through the user's address bar to land back at the application. So I like to think of the back channel as hand delivering a message, where you can walk up to somebody, you can give them a thing, they can see you can see them, you know who they are, you can see they took it, and you can see that nobody else came in and stole it along the way. Whereas sending data via the front channel is more like kind of just throwing it over the wall and hoping it makes it. And this is actually really important because anytime you send data in the front channel, the sender can never actually really be sure that the data made it. But there's also this problem with receiving data via the front channel, which is that you don't actually know where it came from. You can't actually guarantee that it's from the person you think it's from because all you see is this thing comes flying over the wall and you don't actually know who it's from. So neither side is actually getting the complete picture here, which is a pretty dangerous situation to be in, especially if what we're sending in the front channel is an access token. So cross-origin resource sharing wasn't readily available in 2012 when OAuth was first created. So OAuth applications needed a workaround, and that's really where the implicit flow came from. Of course, cross-origin resource sharing is widely available now, so there isn't really this need for the implicit flow anymore because it's solving a problem that doesn't exist anymore. So if you're curious about the implicit flow, there's really no good reason to be using it anymore. And if you want to take a look at what websites are still using it, this is a pretty fun extension. If you install this browser extension, it'll keep an eye on the address bar and look for websites using the implicit flow, which it can tell because all it has to do is watch the address bar to wait till access tokens appear. And then it'll turn a little red icon in the corner and you can see which websites are using the implicit flow. And you can actually then also see the access tokens. If you do find websites using the implicit flow, you should go and tell them to upgrade. Okay, so we had the implicit flow because without cross-origin resource sharing, there wasn't really an alternative for JavaScript apps. But thanks to broad adoption of cross-origin resource sharing, as well as upgrades to the browser cryptography APIs, PKCE is actually a great solution for browsers now as well. So there's another document in the group called OAuth for browser-based apps. And that document is actually recommendations for apps running in a browser. One of the things it says is don't use the implicit flow and instead use PKCE, since it's available now. It also talks about some different options you have for deployment patterns of your applications. So one option is, of course, the sort of static web host model, where you deploy your JavaScript and HTML on a static web host that can't run any code itself. That code is downloaded into the browser and the entire application runs in the browser. In this case, the JavaScript app is a public client because it can't have a secret because you couldn't safely put a client secret in that static web host. And the browser does the OAuth exchange itself. There's another option which you have, which is actually to use a dynamic backend to serve your single page app. And this is actually a pretty common deployment pattern as well, so it's called out in this document also. Neither of these are right or wrong, there's just different considerations to both of them. And in this case, your web app that's serving the single page app can actually be the OAuth client itself, which most importantly means that it can use a client secret. And then you can actually keep all the OAuth flow out of the browser. That way it stays up in the server and it just uses a session cookie to talk between the browser and the web app. All right, so this is where we're at right now. We've got PKCE, OAuth for mobile apps, OAuth for browser-based apps. There's another document called the OAuth Security Best Current Practice. This document is essentially a roundup of all of the best things you can do to make the most secure OAuth system today. And it reiterates things that are in these other specs and references of those other specs, things like don't use the implicit flow, also don't use the password flow. And it turns out there's actually another problem with the authorization code flow. Even if you have a client secret, there's still another problem. And that is solved by PKCE. So actually every application should be using PKCE, not just public clients. And of course, since it's not really safe to put access tokens in query strings, it also takes that out of the bearer token spec. So the Security BCP. There's a lot in here, and it's worth a read, but this basically captures the most secure way to deploy an OAuth system today. One of the things it says is all OAuth clients must use the authorization code flow with PKCE. The specific reason for that is pretty detailed, and I'm going to save that for another video. Actually, this video on our Okta Developer YouTube channel goes into the actual attack. The short version of the attack is because that authorization code is sent in the front channel, it could be stolen and replaced, just like anything in the front channel can, and the client secret actually doesn't quite solve it. We need something else, and that's where PKCE comes in and solves that problem. So if you're curious about the particular attack there, that's the authorization code injection attack, go take a look at this video. It actually goes through a live demonstration of the attack. Okay, one of the other things in this document it says is don't use the password grant. Turns out that's not safe either. We're going to talk about some of the reasons why. So in the spec, it just flat out says the password grant must not be used. It's effectively removing it from OAuth. And there's this pretty dense text which talks about why the password grant must not be used. But before we get into that, the reason the password grant was added to OAuth in the first place was actually as a migration strategy for applications to upgrade to OAuth. So before OAuth, if applications were storing a password and using the password at an API like using HTTP basic auth, then apps had to store the password, and the password grant would give those apps a way to opt in and upgrade into OAuth. So they would take their stored password, exchange it for an access token, forget the password, and now they're upgraded into an OAuth flow. The problem was that people saw the password grant in the spec and said, oh, that means I can build a new application using the password grant, which was never really the intent. It was always meant as a migration strategy. It just looked like it was a valid option for news deployments, and people were doing that instead. So let's talk about some of the reasons why the password grant is so problematic. So for one, it exposes the username and password to the application, which was the entire point of OAuth in the first place. We want to avoid applications handling passwords. Now for third-party apps, the reasons are pretty obvious. You would never trust a third-party app developer to properly handle Google passwords, for example. But even for first-party apps, it's still important. Avoiding applications touching passwords means there's fewer places attackers can try to steal passwords. If you've got password dialogues all over the place, then there's every place as a password prompt, someone can try to steal passwords out of that box. One of the other problems, which is really tricky, is that having password prompts all over the place trains users that it's okay to enter the password wherever. And ideally, we would really not like our users to get phished, right? We don't want users to feel comfortable entering their password anywhere except legitimate places. So the fewer legitimate places there are, the more you can train them to recognize the valid ones. Lastly, and this one's actually really important, especially now, we all know that passwords are not the best security. And we're solving this now by adding things like multi-factor authentication. And in some cases, that's going to be things like a hardware security key or WebAuthn, which is a credential tied to a domain. Now, the password grant doesn't really provide any options to upgrade that to include multi-factor authentication. And in some cases, the multi-factor authentication, like with WebAuthn, it actually can't be shared across apps if they're running on different domains. So the password grant really has no place in OAuth anymore because it really isn't suited to modern authentication. So the Security BCP just says, don't use the password grant. Instead, use a redirect-based flow so that you can do things like add MFA. All right, the next one it says is that redirect URLs must be exact match. Now, this one is actually a pretty old one, and most servers, thankfully, have realized this a long time ago and do this properly. But a while ago, there was these headlines about this attack on OAuth called covert redirect. And essentially what it was is that some OAuth servers were not doing exact match validation of redirect URLs, which would open those servers up to be able to be used in a redirect-based attack. So if you imagine an application is running on exampleapp.com and the OAuth server is configured to allow redirecting back to any URL at that whole domain, if there's an open redirect on that application, so you can actually chain this together and then the user can land at your attacker's website when visiting a link that otherwise looks valid. So exact redirect URL matching is a pretty commonly known thing now, and most servers require exact matches. The security best practice is really just putting that stick in the ground and saying, you have to do it this way now. All right, by now you're probably thinking, wow, that was a lot. This is really complicated. There's a lot of documents flying around. How do I even begin to make sense of them? And you're not wrong. It can feel like trying to get through a maze. There's a lot of documents in the OAuth space because of how much it's evolved over the years. But one of the nice things is that if you actually look at what we've got here, we've got OAuth core plus PKCE plus these other RFCs plus the Security BCP, which actually takes a bunch of stuff out. If you condense all of that, what you're actually left with is a much simpler picture. You actually just have the auth code flow with PKCE, always, no conditions. You got the client credentials grant, and then you have two different ways to use access tokens. So this is OAuth 2.1. The idea with OAuth 2.1 is we're going to consolidate all these documents and rewrite them into a new starting point. The idea is to capture all of the current best practices in a new name. That way when we say OAuth 2.1, we all know what options of OAuth 2 we actually mean. One of the other goals with OAuth 2.1 is that OAuth 2 actually left a lot of things open for interpretation and a lot of extension points. And some of those extension points have now been filled. There are extensions for things like structured access tokens or mutual TLS or dynamic client registration, things that didn't exist when OAuth 2 was first published. So when you're reading OAuth 2, there's a lot of missing pieces and holes that you're like, well, now what? Where do I go to find out more? So what we're doing with OAuth 2.1 is actually referencing out those existing extensions at the appropriate places in the spec. So OAuth 2.1 isn't going to roll up everything. It doesn't include all of the specs in the OAuth world. It's just those core ones that we talked about. But it will then reference and link out to a bunch of extensions that do exist so that you can find them if you want to read more about them. Some things that OAuth 2.1 is not doing. We are not defining any new behavior in OAuth 2.1. The idea is that OAuth 2.1 is the best way to do OAuth 2.0. So everything that's already documented in the Security BCP, as well as a couple of other extensions like PKCE, those are being brought into OAuth 2.1. New behavior is not defined in 2.1. We also don't want to include extensions that are experimental or not yet widely deployed, because we really just want to focus on what is the most secure way to do OAuth at its core. So OAuth 2.1 is a consolidation of this list of RFCs. It defines the authorization code grant and the client credentials grant. The authorization code grant, of course, includes PKCE. It requires exact redirect URL matching. It also says no access tokens and query strings, because we all agreed about that a long time ago. And because the Security BCP says it, this also places some new restrictions on refresh tokens for single-page apps. Mainly that single-page apps, if they do want to use refresh tokens, those refresh tokens need to be one-time use or sender constrained. And the implicit grant and the password grant are left out of 2.1. So the Security BCP actually says you must not use the password grant, must not use the implicit grant. So we're just not including them in OAuth 2.1. They're being taken out of OAuth. So one of the other things OAuth 2.1 is doing is trying to clean up the language in the spec. And if you look at the OAuth 2.0 spec, there are two client types defined. This is public clients and confidential clients. Now, public clients are apps that can't use a client secret, or actually can't be deployed with a client secret. Traditionally, that's going to be things like JavaScript apps and mobile apps. So again, if you try to put a client secret in a JavaScript app, it's not going to be secret for very long. Same is true with mobile. You can't put a client secret in a mobile app, publish it on the App Store, and then have it remain secret. Confidential clients are apps that can use a client secret and can be deployed with a client secret. Traditionally, those are web applications, things like Java, .NET apps, right? Where you can put a client secret in the app's configuration and it will remain secret. Now, one of the really important aspects of this is that that client secret is doing two jobs. The first job it's doing is authenticating the client, but the second job it's doing is proving the app's identity. And this is where there's this sort of middle ground between the two. So we're defining a new term in the spec called Credentialed Client. Now, a Credentialed Client is an app that does have credentials, but whose identity is not confirmed. So you might be thinking, what on earth could cause that? Or what would be a Credentialed Client? Well, probably the most realistic way that this could happen is using dynamic client registration. So if you imagine a mobile app is shipped in the App Store, there's no client secret in it, someone downloads it, the first thing it does is it uses the dynamic client registration endpoint to register itself, and it gets a client secret. unique to that instance of the app. Now, that registration call is unauthenticated. Anybody can make that call, and anybody can impersonate that API call, which means that client secret doesn't actually prove that application's identity. But it does serve all the other jobs of a client secret, which is authenticating any requests the app makes to that instance of the app. Okay, so why do we need a new term for this? Well, if you look at the existing language in the OAuth 2 spec, you'll see this distinction has already been made in the spec. For example, this sentence, if the client type is confidential or the client was issued client credentials. If the only way that clients could have been issued credentials were confidential clients, that second part wouldn't have needed to be there. So clearly this distinction was already being called out in the OAuth spec, it just hadn't been given a name yet. And this kind of thing happens in a few places in the spec. So if we replace that with credentialed clients, it just cleans up the text. So now the text can say confidential or credentialed clients must authenticate. So in OAuth 2.1, there are now 3 clients based on whether or not they can authenticate and whether their identity has been proven. Public clients have no credentials, so they can't authenticate. Their identity also can't really be confirmed. Credentialed clients can authenticate, but their identity is not confirmed. And confidential clients can both authenticate and their identity has been confirmed. Typically, the confirmation of identity of that app is established when the app developer goes and registers the app in the developer portal. And of course, that registration step happens when the developer is actually logged in. So the developer's identity is then tied to that application's identity. One of the places where app identity becomes really important is actually in the OAuth consent screen. So when the user is presented with a dialog like this, saying this application is trying to access your account, do you want to allow it? Well, it's really important that the user knows which app is trying to access their account. So in this example, it looks like Google Docs is trying to ask for permission to access data in your Gmail account, which if you think about it for a second is a little bit weird because those are both Google products. And it turns out that's actually what happened here, is that this application's identity had not been confirmed because it was possible for a developer to go to the Google Developer Console and just register an app and name it Google Docs. And this actually was a huge deal. There were a lot of headlines going around about how Google had been hacked, essentially. And it wasn't really a hack, it was a legitimate OAuth exchange just with a fake app. Or it wasn't even a fake app, it was a real app. It just happened to be named Google Docs. So Google has put a lot of measures in place to prevent this kind of thing in the future, doing things like requiring manual review before applications are published and restricting which scopes applications are allowed to request. And that's all part of that idea of validating the identity of these applications. All right, so that is a summary of OAuth 2.1, which is essentially the most secure way to deploy an OAuth system today. OAuth 2.1 is still in active development in the OAuth working group. It was recently adopted as a working group item, so we are now actively working on it and looking for feedback. So please give it a read, and if you do have any feedback, feel free to email me directly, get in touch with me on Twitter, post to the OAuth mailing list, or file a GitHub issue. We really want this to be a much easier way for people to learn about OAuth and implement OAuth more securely from the beginning. I would rather that you only need to read one document than having to go through 10 years of documents figuring out which ones are important. So that's really my goal with OAuth 2.1, which is to make things just a lot simpler to understand and make them more secure by default. Thank you so much for watching. I hope you got something out of this talk. Feel free to get in touch with me on Twitter if you have any questions. And if you would like a copy of my book, you can find it at oauth2simplified.com. Thanks.